So we want to find all the zeros of a polynomial function. And to some degree, this lesson will seem redundant because we will be doing a lot of the things that we've already been doing over the last couple of lessons. But there will be some new ways to look at the search for zeros and some new tools in searching for the zeros. So remember the good old days when we had functions that looked like y equals 3x squared minus 13x minus 30. And all we had to do was look for two zeros, which meant in a quadratic trinomial, it just meant having to factor. So you run this through the factoring algorithm and you discover that the factors are x minus 6 and 3x plus 5. Set it equal to 0, use the zero product property, and you get x equals 6 and x equals negative 5/3. And those would be the roots or the zeros of that polynomial. Life was good, we moved on. Now, not so much, because we want to start dealing with functions that look like y equals x cubed plus 2x plus 1. Oh, that almost looks like a quadratic trinomial, but it's not. It's a quadratic cubic function. And already we know we can't factor this. We don't have a quadratic formula for this. We don't have a lot of tools at our disposal, except we do have synthetic substitution or synthetic division. Problem is, there are a lot of possible choices for trying to factor this. First thing we want to do is narrow those choices down. Now, you would have seen this in Algebra 2 already, but let's go ahead and go over it again. So the first thing we want to do is try to figure out what the factors could be. Even though we're going to get a lot of extra choices to check, at least if we narrow the choices down to a set of possibilities that the factors are in, then we can work from there, and we're not going to spin our wheels even trying things that are definitely not there. So in this case, I want to look at the the leading coefficient and the constant terms. This one's going to be simple because I need all of the factors of this first leading coefficient. And in this case, it's 1. So 1 is a factor, and I want to take the positive and negative expression of that. So the same thing here with the constant. Plus and minus 1 are the only factors of the constant. And then I want to use the rational zero theorem. And the rational zero theorem just says what it sounds like it's saying. It is a way to find the rational, which would be functions or numbers that could be written in the form of an integer over an integer. So if this function has any rational zeros, meaning any zeros that are written this way, an integer over an integer, the rational zeros theorem will give you a set of numbers in which that zero is contained. And while that was rather jerkily said, I think it was well said. So let's look at some possibilities. The rational zero, an integer over an integer, of any polynomial will be some form of p over q, where p and q are both integers, and p is a result of factors of the constant term, and q are factors of the leading coefficient. Okay, so what does that look like in practice? In this problem, I'm not going to do an example with this problem because it's so simple. I just use that to build the concept. But I do want to try it with this function here that we started with. So if I look at the f of x equals x to the fourth plus 4x cubed minus 12x minus 9, I can see that the leading coefficient, of course, is 1, and so the factors of the leading coefficient are plus and minus 1. But the factors of the constant term are plus or minus 1, 1, plus or minus 3, and plus or minus 9. So we only have 3 factors, well 6 if you include the positive and the negative. But now I want to look at the ratios that I might be able to build out of this. So I'm looking at the leading coefficient has to be the denominator, which means really these are my 6 choices. So all 6 are not factors. All 6 are not going to give me zeros of the function, clearly, because there are only 3 and at most 4, or excuse me, there are 4 and at most 4, but I know that I only have to try 6 different values to find the real zeros of this function, because, excuse me, the rational zeros of this function, because I'm guaranteed by the rational zero theorem that these are them, that they're contained within this set of values. So let's go ahead and try to find some using synthetic division. And this will be one of those situations where you'll want to be sure you're using either a pencil or a really good erasable pen. So let's go. First, I want to make sure I have every value of every x configuration listed, and I do, 4, 3, 2. Oh, I don't have a square, so I want to take all the coefficients, so that means I'm going to have a 1 that goes with the x to the 4th, a 4 with the x cubed, a 0 for x squared, a negative 12 for x, and a negative 9. And then I'm going to try one of these. So I'm going to try 1 because it's the easiest one. Why wouldn't you start with the easiest? Bring down a 1, 2, 4 plus 2 is 6. 1 times 6 is 6. Bring down the 6. 6 times 1 is 6. Minus 12 plus 6. I can already see it's not going to go well, but let's do it anyway. Minus 12 plus 6 is a negative 6. 1 times negative 6 is negative 6. I'm going to get a remainder. It might be worth it to go ahead and finish up just so that I can make a note that the f of 1 equals negative 15. But I want to go ahead and erase all this because that's not a factor. Negative 1. Bring down my 1. Negative 1. That means 3. Negative 3 plus 0 is negative 3. Times 1 is a positive 3. Or I should say times negative 1 is a positive 3. Subtract 12 is negative 9. Times negative 1 is a positive 9. Subtract 9 is a 0. So I know now that one of my factors is x plus 1 as a factor. A 0 is negative 1 and a factor is plus 1. So it'd be lovely if I could then just go ahead and factor the rest of this out, but really I'm going to end up with a cubic term, right? I'm going to have a constant, x to the first power, x to the second power, x cubed. And I don't really have easy ways to go about doing that, so I'm going to go ahead and just run it through the algorithm again. Now, I know that 1 is not a factor. So, or excuse me, 1 is not a solution or a root or a 0. So I'm not going to try it again. The sad state of facts are that negative 1 could still be another factor because we end up with things that look like this, right? X plus 1 squared, which leads to x equals minus 1, but I really had 2 factors that led to that. And remember, on a graph, what that means is you just get a kiss. It would just come down, graph would come down and just touch and turn back around. So that's a possibility. I could try negative 1 again. Oh, what the heck. I'm going to go ahead and do it so that I know that I've exhausted every possibility. So I have a bring down a 1 times negative 1 plus 3, positive 2, times negative 1 plus negative 3 is a negative 5, times negative 1 is a positive 5. Oh, that was a mistake. I should have known better. But at least now I know. So let's try 3 this time. I've exhausted my 1s. So I'm going to bring down a 3. Times 3 is 9. Plus 3 is 12. Times 3 is 36. Take away 3 is 33. Times 3 is 99. Take away 9 is 90. That didn't work, but let's go ahead and, just in case I need it, record the value. Equals 90. All right, let's try negative 3 now. I know there's a lot of busy work here, but it's better than guessing. I would have already had to go through the 2's if I was just trying to go from the smallest to the greatest, so might as well just keep going. 1 times negative 3 is negative 3. 0 times negative 3 is 0. Negative 3 times negative 3 is a positive 9. At last, a 0. So now I know that I have two factors. I have x plus 1 and x plus 3 are factors, and now I definitely have a quadratic, so I can just go ahead and solve this one the old-fashioned way. So I can say 0x, and this is going to be x squared. So I have, oh, well actually this finishes the job completely. So one factor is x plus 1, and then x plus 3, and then x squared minus 3 is a factor. So if I want to find rational factors, this is all I can do. I also have this factor here, which tells me if I set this equal to 0, this last factor would give me x squared minus 3, which is equals 0, which is x squared equals positive 3, so x equals plus or minus the square root of 3. So look what I've got here. I have two factors, x equals negative 1 and x equals negative 3, that are rational zeros, because these could be written as an integer over an integer just by putting a 1 underneath them. So these are rational zeros, and that's what the rational zeros theorem promised. And that was all I was able to find, was the rational zeros. But look at the other 0. Look at what I got here. This is two zeros, plus n minus the square root of 3. These are actually called irrational zeros because the square root of 3 is an irrational number. There is no way to write this number as an integer over an integer. So these are the irrational zeros. But what we really care about is we've found all the zeros. I have two rational, two irrational, total of 4 expected. Done. Happy to be finished. So let's look at another problem, and well, let's talk for a second before we do. So when we're looking for zeros of a polynomial that isn't a nice, neat little quadratic trinomial or a quadratic binomial, we have to use other tools to reduce the polynomial down to a quadratic, so that we can use the tools we already have. And so synthetic division is a really powerful way to do that, except we would be left guessing and checking using synthetic division without some sort of a clue as to what the zeros would be. And the rational zeros theorem tells us, at least, even though in this case I had to look at 6 different, or I might have had to look at 6, I actually looked at 4 different values. Eventually I was able to whittle it down so that I could just factor straight out, or actually take what I got in this case and find the irrational zeros. But it lets me winnow away at the rational zeros before I have to pull out some other tools. But still, sometimes functions have a lot of possible zeros. And I'm going to show you one now, and we'll talk about a couple of ways that we can even make the list even smaller, so that we're still guessing and checking, but it's very, very educated guessing and very, very educated checking. So let's look at the function, let's see, f of x equals 3x cubed minus 7x squared minus 22x plus 8. So the leading coefficient in this case is 3. And the constant is 8. And I'm going to write all of the possible zeros down. This is example number 2 in your textbook on page 120. So if you're still a little bit iffy about finding these values, you can look in the book and refresh your memory. But I'm going to save a little time on the video. So we have possible zeros are plus n minus 1, plus n minus 2, plus n minus 4, plus n minus 8, plus n minus 1/3, plus n minus 2/3. Holy moly, I'm running out of room here. Plus n minus 4/3, and plus n minus 8/3. Okay, so clearly we don't want to have to do this with the fractions if we can get away with it. But even if we're looking just at the integer values, it starts to be a pretty daunting list for trial and error. So what can we do to sort of eliminate some of these values so that we don't have to try as many out? Well, one way is to open up a graphing utility, and I've already set this up with this graph. You can see that the function in my calculator is exactly the same function as on the notes. And if I graph this, I see the function here. I see that there are 3 roots on the graph, and if I can figure out the boundary, the lower bound and the upper bound, within which my actual roots or zeros fall, then I might be able to eliminate some outside that bound that fit the criteria for the rational zeros theorem, but don't have to be checked because they're not going to work in this situation. And so I certainly can do that using the trace tool. So where is my trace? Let's see. Here we go. So if I trace along my graph, I can see here that I'm getting really close to 3.9, so I'm imagining this is somewhere around 4. So I don't really know if it's less than 4 or greater than 4, and if I trace closer, and I don't want to zoom in to do that, you guys know how to use your calculators in Desmos, you can certainly figure that out. But I'm going to say it's pretty safe to assume that I don't have to check plus or minus 8. Right? Because that's, well, I don't know about minus 8 yet, but I don't have to check plus 8. So let's zoom or trace to the other side of the graph. It's going to take me way over here. So here again, I'm looking at being somewhere between negative 1.8 or negative 1.6. Oh, I went the wrong way. Or negative 2. So I'm thinking this is going to be somewhere around 2 on the negative end. So I certainly don't have to check negative 4 because that's outside my bound, and I don't have to check any of the 8s, positive or negative, because that's outside my bound. Well, 8/3 is the same thing as 2 2/3, which is outside my negative bound. And let's see, that's 1 1/4. I think these all I have to check. So I've already eliminated a bunch of them. You could even do that in a regional way. We can look at the fact that I only have one negative number, so I might look for my negatives first because then I can eliminate that one, and then I can eliminate anything that falls inside of, or any other negative number, because there's only going to be one. So I could look for that first, and when I found it, I know I'm there. So really, whenever I'm working with my rational zeros theorem, one tool, if it's available, is to graph it on a graphing calculator and look for the bounds and eliminate some extras. And then one other tool that you might find useful, I don't tend to be quite honest, but it's a pretty important tool as powers or as polynomials get bigger and you have bigger and bigger values. And so at the pre-algebra level, pre-calculus level, we're really dealing with numbers that you can handle pretty readily using the tools that I've already shown you. But I'm going to go ahead and show you this one. It's called the Descartes rule of signs. And this is the same Descartes that the Cartesian plane is named after. and it gives you a description of the number, or it tells you how many positive and how many negative zeros there are going to be on a function. And that can be useful if you've already found one negative zero and you know that there is only one negative zero, then you don't have to try any of the other possible zeros that the theorem gives you. So it is a useful tool, but generally we're dealing with polynomials of such a small degree that you easily get to the quadratic trie or binomial and can finish it up on your own. But let's look at what it says. It says that f of x, or the number of positive, I'm going to use shorthand, of positive zeros is equal to the number of sign changes in f of x. So we remember from this picture just a moment ago that we have two positive zeros on this function. So let's test the Descartes' rule of signs against that. Well, if I go from the first term to the second term, this is a plus and this is a negative. So this is a positive term and this is a negative term. So that's one sign change. The next term is negative, so I don't really care. But this, to go from this term to this term, I've changed my sign again. So notice I have two sign changes in f of x, and as predicted, I have two positive zeros. That's pretty cool. It actually is really handy. I know I kind of poo-pooed it a minute ago, but it's really handy. Then there is a corollary rule, or another rule, that says the number of negative zeros equals the number of sign changes in the f of minus x. So back up here, if I put in negative x for everything, I get, well, negative x is going to be, negative x cubed is going to be negative, so this is going to become negative 3x cubed, minus, well, negative x squared here is just going to be positive, so I'm going to keep the same, minus 7x squared. If I put in a negative x, this is going to become a positive 22x, and then 8 doesn't change at all. So let's look at our sign changes now. I have a negative to a negative. Oh, here I go from negative to positive, and then I'm positive again. So I only have one sign change in the f of minus x. Pull up my graph again. One sign change, that's my zero right there. I have a negative 0 predicted by Descartes' rule of signs, and then I have two positive zeros predicted by Descartes' rule of signs. Okay, so basically all we've done here today is we have looked at ways to, we're still finding zeros exactly the same way using synthetic division, but we've looked at ways to narrow down and begin to eliminate all the possible choices of values for testing by synthetic division. I have the rational zeros theorem, which tells me what a rational zero has to be if it is a zero of a function, and then I have Descartes' rule of signs that tells me how many positive and how many negative, so I can eliminate, after I find one negative, if I'm expecting one negative, I can eliminate all the rest of them and not even have to try them in the synthetic division. And if I use my graphing calculator, I can look at the boundary on which my zeros exist and eliminate values that fall outside of that boundary.